Hello and welcome. This video is the 13th and the 14th video in the P3 Force of Motion Flip Learning series from Darton College's Science Department. My name is Mr. Clee. Right, the aim of this lesson is that by the end of it you should be able to calculate an object's weight from its mass. We should also be able to explain why drag increases with speed and describe and explain the motion of an object as it falls under gravity, including the idea of terminal velocity. That means as an object falls, what happens to its speed in a gravity field. Obviously when an object falls not in a gravity field, different things happen. Explaining also, linking the drag one here, why drag increases, to how the shape of an object affects drag and terminal velocity. Right, the first thing, the really important thing that we need to just make completely distinct is the difference here between the ideas of mass and the ideas of weight. Mass is a constant. Mass is how much matter you are made up of in kilograms. The difficulty comes that when we talk about weight, we often talk about kilograms, and that's wrong. It's not scientifically accurate to talk about weight in those terms. That's mass. That's how much matter you are made up of. Your weight is basically, on a simple level, how gravity acts on your mass. So weight is a force. And because weight is a force, it is measured in newtons. In order to find out your weight, you have to take your mass and multiply it by gravity on the planet or the body that you're on, which on Earth is 9.8. We approximate that to 10, and that gives you your weight. So basically speaking, your weight is 10 times your mass in kilograms. So if you weigh 25 kilograms and we assume gravity to be 10, then that will give you a weight of 250 newtons. Right, so the gravity on a planet like Earth is dependent on the mass of the body, of the planet that we're talking about. At any point on Earth, the gravity is roughly the same. We can assume it's the same. So because of this, the speed that an object accelerates to as it falls is equal to the gravity. So wherever you are on the planet, you fall at the same rate. All objects accelerate at the same rate. You might think, well, that's not true. I've seen that happen. I've seen things fall differently. The reason that things fall differently is because of air resistance and because of their shape. If you take away air resistance, you take away that friction and that drag, then all objects fall at exactly the same rate. That's exactly what's been done in this series of images here. This feather and the ball are both falling in a vacuum. So we've taken away air resistance, and you can see that the distance between the positions in each of these images is the same as each other. That means that these objects are falling at the same rate because they are falling in a vacuum. They're falling at the rate of at the same rate that gravity acts, and because air resistance has been taken away, that means that acceleration is constant. I did say before that gravity was constant. It's not strictly true. It's all to do with, as well as the mass of the object, it's also to do with the distance between the two masses. So if you are at the top of Mount Everest, then the force of gravitational attraction from the Earth, because you're further away from it, is slightly less than if you were sat down on the beach sunbathing. Because of this, if you were to fall off Everest, you'd fall slightly slower than if you were to fall at ground level. Not that it would make much difference to you. So because it's all linked to mass, there are differences on different bodies as to what the force of gravity is. On Earth, it's as I said previously, it's roughly 10 newtons per kilogram. Whereas on the Moon here, it's about a sixth of that. It's about that would be about 1.6 newtons per kilogram. So just a really simple calculation to see if we can do that. A car has a mass of 1,450. What's its weight? if we assume that gravity is 10, then that means that the weight of the car in newtons, because it's a force, is 14,500 newtons. So this explains what we looked at previously in the sense of how an object falls through a fluid. When an object falls through a fluid, like gas, like liquid, that means that there is drag, there is a reaction force. There is a force going upwards. You can see it labelled in the diagram here as air resistance. And the air resistance changes in response to speed. So the faster you are, the more air resistance there is. To start with, there's very, very little air resistance, so the leaf gets faster because the force of gravity or its weight is pulling it down. The air resistance, as it increases, gets faster and faster and faster until we get to the picture here, the image there, where the air resistance has increased so it is equal to the weight. When it's equal to the weight, the speed of the leaf will no longer increase. With things like leaf, this happens very, very quickly. That's why they float to the ground quite slowly. Same thing here with a skydiver. At the start of his jump, there is no air resistance because there is no movement. So he starts to accelerate down because of his weight. As he gets faster and faster, this air resistance gets bigger and bigger. When these two forces are equal to each other, we call this terminal velocity. That means that he is basically going at his top speed. The reason that he slows down when he opens his parachute is because he massively increases the area that the drag can act on. Because he increases the area that the drag can act on, then what you end up having is this huge resistance. That slows him down a lot. That will then decrease, that air resistance will then decrease until it's again the same as his weight and equal. The parachutist is falling at another terminal velocity, but a lower terminal velocity before a much more reasonable terminal velocity in terms of landing. I think it's probably important to point out that at this point, because whenever you see people open parachutes, you do so from the perspective of somebody else falling next to them. It always looks from that perspective that when you open a parachute, you go back up. That does not happen. You don't go back up when you open a parachute. You just appear to be going back up from the viewpoint of the person filming you. You go down still, but you just do so much slower. One idea, one key word that we need to get in here is this idea of resultant force, which is basically leftover force, I suppose. It's when you take into account the weight and the drag, what is the leftover force. If there is zero leftover force, then what we have there is a terminal velocity. This hasn't come across very well, but basically, when moving horizontally, the same thing applies. When you have thrust from an engine, you get drag from the water or from the air if you're in a car. The engine can only provide a certain amount of thrust, and as you get faster and faster and faster, the drag will increase until these two forces are equal to each other. The resultant force is 0 newtons, and we have a boat travelling at a terminal speed, exactly the same as what we're talking about when we're talking about a falling object, apart from this is something moving horizontally. So, in summary, weight is equal to mass times gravity. On Earth, that's basically 10 times the mass is equal to the weight, or actually 9.8. Drag is a reaction force. It increases with speed because movement creates it. Falling objects will accelerate as it falls. Acceleration will decrease. It will continue to get faster, but the rate of increase in speed will slow until the object stops accelerating and reaches its terminal velocity, its top speed. And we can reduce drag and terminal velocity by increasing the streamlining of the shape, by creating an aerodynamic body. Thank you very much for watching. This video is covering 2 lessons. It's covering Tuesday the 20th and Wednesday the 21st of May's lessons this week. Thank you.